10 scientific mysteries continue to baffle the world's leading researchers in 2025. Some have puzzled humanity for millennia, while others emerged from cutting-edge discoveries just last year. In 2024, astronomers detected ASCAP J1832-0911, an object emitting bright flashes of radio waves and X-rays every 44 minutes, a phenomenon that represents an entirely new class of cosmic objects we cannot explain. These aren't obscure academic questions. They're fundamental problems that could reshape our understanding of physics and biology. We'll start at the dawn of everything, where cosmic expansion theories still fail, then zoom in on our cosmic backyard before venturing to the farthest reaches of space. The creation of the universe, updated Big Bang theories. How did everything begin? This question has haunted humanity since the first conscious minds gazed upward at the night sky. We've built the most sophisticated instruments ever conceived to peer back through time itself, yet the ultimate origin of existence remains stubbornly beyond our grasp. The James Webb Space Telescope delivered unprecedented data throughout 2024 and into 2025, revealing galaxies that formed just 400 million years after the Big Bang. Webb's 2024 data showed several galaxies at 400 million years after the Big Bang with stellar masses up to 100 billion suns, more mature than models allow. These observations confirmed that cosmic expansion happened exactly as predicted, but they also created new problems. These early galaxies appeared too massive and too organized for their age. Planck's CMB data gives us a 13.8 billion year estimate with plus or minus 40 million year accuracy. But this precision makes the deeper mystery more acute. We can trace cosmic history back to when the universe was smaller than a proton, yet we cannot explain what came before that moment or what caused the initial expansion. Eternal inflation theory suggests our Big Bang was just one bubble in an endless foam of expanding universes. Even eternal inflation models admit a beginning. Goose calls it a cosmological stuck point. This highlights that we still need a cause for the start. Meanwhile, cyclic universe models propose that our cosmos goes through endless cycles of expansion and contraction, making our Big Bang just the latest in an infinite series of cosmic rebirths. Quantum field theory offers a different approach to the initial singularity problem. New proposals suggest that quantum vacuum fluctuations could spontaneously create space, time, and matter from absolutely nothing. These theories mathematically describe how the fundamental fields of physics might bootstrap themselves into existence, generating the energy density needed for cosmic inflation. The question, why is there something rather than nothing, grows more perplexing as our knowledge increases. Philosophers and physicists have grappled with this puzzle for centuries, but modern cosmology makes it more urgent. Every equation we write assumes the existence of mathematical relationships, physical laws, and the very concept of existence itself. Multiverse theories complicate creation stories further. If our universe is just one of countless others, each with different physical constants and histories, then asking about the creation becomes meaningless. Goose warns multiverse scenarios still require beginning, so the origin remains unsolved. Even with gravitational wave detectors, particle accelerators, and space telescopes that can see nearly to the beginning of time, we face a fundamental barrier. The laws of physics break down at the moment of creation. General relativity predicts infinite density and curvature, while quantum mechanics suggests that space and time themselves emerge from more fundamental processes we cannot yet comprehend. Current physics may be inherently incapable of solving the creation mystery. The very tools we use to investigate reality might be products of the process we're trying to explain. This creates an endless loop where we use the consequences of creation to understand creation itself. Yet even as we struggle with cosmic origins, we face an equally perplexing puzzle about the very substance that fills our universe. Dark Matter's True Nature 2025 detection attempts. 85% of all matter in the universe is completely invisible to us. This invisible substance, called dark matter, outweighs all the stars, planets, and gas clouds we can see by more than 5 to 1. Yet after decades of intensive searching, scientists have never directly detected a single dark matter particle. The Lux Zeppelin detector, buried nearly a mile underground in South Dakota, represents the most sensitive dark matter hunting experiment ever built. Throughout 2025, this massive detector filled with liquid xenon has been monitoring for the faint signal that would indicate a dark matter particle colliding with an atomic nucleus. The underground location shields the detector from cosmic rays and T-rays. Other interference, creating the quietest environment possible for this cosmic ghost hunt. Despite running continuously with 1,000 times increased sensitivity over Xenon 1T, Lux Zeppelin has detected nothing beyond ordinary background radiation. Scientists know dark matter must exist because of its gravitational effects on visible matter. Galaxies rotate too fast to hold together based on the mass of their stars alone. Galaxy clusters bend light from distant objects more than they should. Computer simulations of cosmic structure formation only work when researchers include 5 times more dark matter than ordinary matter. The gravitational signatures are undeniable, but the particles themselves remain stubbornly hidden. The most promising candidates for dark matter particles have failed to appear in detectors. Null results at current cross-section limits below 10 to the power of negative 47 cm client for 40 GeV WIMPs pushes scientists towards sub-GeV candidates. Axions, hypothetical particles that could solve problems in both particle physics and cosmology, have similarly evaded detection despite specialized experiments designed to catch them. Each negative result forces scientists to consider more exotic possibilities. Modified gravity theories offer alternatives to dark matter, though they face significant challenges. Modified Newtonian dynamics explains galaxy rotation curves, but struggles with galaxy cluster observations, limiting its acceptance compared to dark matter models. Emergent gravity theory suggests that gravitational effects arise from quantum entanglement in ways that could eliminate the need for dark matter entirely. The Euclid Space Telescope completed its first comprehensive dark matter map in 2024, revealing unexpected structures and how this invisible matter is distributed across the universe. Euclid's 2025 data reveal clumped dark matter filaments thicker than predicted, suggesting self-interaction or novel physics. Some regions show less dark matter than expected, while others contain surprising concentrations. Recent proposals suggest dark matter might have complex self-interactions that we have not considered. If dark matter particles can collide with each other, scatter, or even form bound states, this could explain the unusual distributions Euclid observed. This self-interacting dark matter could create cores in galaxy centers and alter the predicted structure of cosmic web filaments. Primordial black holes formed in the early universe represent another dark matter candidate gaining attention. Current studies limit primordial black hole mass to 10 carat 17 to 10 carat 23 grams, though constraints remain uncertain. Recent gravitational wave detections have renewed interest in this possibility. Artificial intelligence systems are analyzing vast datasets from dark matter simulations in 2025, searching for patterns that human researchers might miss. Phantom data from Lux showed noise patterns matched atmospheric muons, not dark matter, prompting new machine learning methods to isolate true signals. These AI systems process thousands of simulation results simultaneously, testing scenarios that would take human scientists years to evaluate. After more than 50 years of searching with increasingly sophisticated detectors and theories, we remain as mystified by dark matter as when astronomers first noticed galaxies spinning too fast. The universe's most abundant substance continues to hide from us, leaving scientists to wonder if the answer lies in physics we have not yet discovered. Yet, while we struggle to understand the cosmos around us, an equally profound mystery exists much closer to home: consciousness and the hard problem, latest neuroscience. How does 3 pounds of brain tissue create the rich inner world of thoughts, emotions, and experiences that define human existence? This question represents neuroscience's greatest challenge, explaining how electrical impulses between neurons somehow generate the subjective experience of being conscious. fMRI and optogenetics tracked activity clusters in brain circuits with unprecedented precision in 2025. High-resolution fMRI scanners can now monitor neural networks firing in real time, while new optogenetic techniques allow researchers to control specific brain circuits with light. These technologies reveal intricate networks of communication across different brain regions, but they still cannot explain why these neural processes feel like anything at all. The hard problem of consciousness, coined by philosopher David Chalmers, remains as puzzling today as when first articulated. Scientists can explain how the brain processes information, responds to stimuli, and controls behavior. These are the easy problems of consciousness. But explaining why we have subjective experiences, why seeing red feels different from hearing music, or why physical pain creates genuine suffering continues to elude scientific explanation. The Perturbational Complexity Index represents a breakthrough. Attempt to measure consciousness objectively. This technique sends magnetic pulses into the brain and measures how the resultant neural activity spreads and integrates across different regions. Conscious patients show complex, sustained patterns of neural response, while unconscious patients exhibit simple, localized activity. Researchers are now using PCI to assess consciousness in patients with severe brain injuries, potentially revolutionizing how we understand disorders of consciousness. Psychedelic research has exploded in 2024, providing unprecedented insights into altered states of consciousness. Studies with psilocybin, LSD, and DMT show that these substances temporarily disrupt the brain's default mode network, a collection of regions active during rest and self-reflection. Participants report profound changes in subjective experience, including dissolution of the sense of self in mystical experiences. These findings suggest that normal consciousness might be just one possible configuration of brain activity. Two major theories compete to explain consciousness. Global workspace theory proposes that consciousness arises when information becomes globally available across the brain through a network of interconnected regions. Integrated information theory takes a different approach, suggesting that consciousness corresponds to integrated information, the amount of information generated by a system above and beyond its parts. Both theories make testable predictions, but neither fully explains why integrated information or global access should create subjective experience. Artificial intelligence systems in 2025 can engage in sophisticated conversations, solve complex problems, and even create art. Large language models process information in ways that sometimes mirror human cognition, yet they lack genuine subjective experience. These systems respond to questions about consciousness, but they have no inner mental life. The gap between information processing and genuine experience remains as wide as ever. Split brain research continues revealing surprising aspects of conscious unity. Patients who have had their corpus callosum severed to treat epilepsy sometimes show conflicting behaviors between their left and right hemispheres. Recent studies suggest that consciousness might be more fragmented than we assume, even in healthy brains. These findings challenge our intuitive sense that consciousness is unified and indivisible. The philosophical implications are profound. If consciousness cannot be reduced to neural activity, it might represent a fundamental aspect of reality that science cannot fully capture. Some researchers propose that consciousness might be the one thing that will always remain beyond complete scientific explanation. Yet, while we struggle to understand the nature of inner experience, other mysteries manifest in ways that affect people's daily lives in very tangible ways. The Taos Hum new 2024 investigation results. Residents of Taos, New Mexico describe it as a persistent, maddening sound that invades their homes and minds. This low-frequency hum disrupts sleep, triggers headaches, and creates psychological distress for those unfortunate enough to hear it. The sound becomes more noticeable indoors and at night, turning what should be peaceful environments into sources of torment. Some residents have lived with this acoustic torture for decades, unable to escape the constant droning that seems to emanate from nowhere and everywhere at once. Local and global hum reports prompt investigations into infrasound and electromagnetic origins, though no consensus has emerged. Researchers used infrasound sensors in GPS-linked microphones in 2018 to 2023 to map hum reports but found no clear source. Teams of acoustics experts worked around the clock, collecting data during different weather conditions, times of day, and seasonal variations. Despite intensive monitoring, the source of the hum remained elusive. The hum affects roughly 2% of the population, a small but significant group that experiences genuine physical and psychological suffering. These individuals report chronic insomnia, persistent headaches, and mounting psychological distress that can lead to anxiety and depression. The selectivity of the phenomenon puzzles researchers. Why can some people hear the hum clearly while others standing next to them detect nothing? Medical examinations of affected individuals show no consistent hearing abnormalities or neurological conditions that might explain their sensitivity. Hum investigations consider geological, industrial, and auditory pathologies but remain inconclusive. New Mexico's complex geological structure, including the Rio Grande Rift system, could generate low-frequency vibrations through underground rock formations. Industrial sources like power lines, transformers, and manufacturing facilities produce electromagnetic fields and mechanical vibrations that might contribute to the phenomenon. Some researchers explore whether certain individuals possess heightened sensitivity to these environmental factors. Global Hum reports since 1993 in Taos, Auckland, and Windsor have been the subject of tinnitus machinery and seismic hypotheses. The Australian cases emerged near mining operations, while Canadian reports clustered around areas with significant underground geological activity. These global occurrences suggest that Taos Hum represents one instance of a broader phenomenon affecting multiple locations with seemingly different environmental conditions. Traditional audio equipment consistently fails to detect the frequencies that sufferers clearly hear. Standard microphones and recording devices cannot capture the specific characteristics of the hum, leading to frustration among both researchers and affected residents. This technical limitation has complicated scientific investigation and contributed to skepticism about the phenomenon's reality. Some studies suggest placebo or frisson responses could explain individual reports, though researchers documented measurable physiological effects in people exposed to the hum, including elevated stress hormones and disrupted sleep patterns. These objective measurements prove the hum creates genuine physical responses rather than purely psychological reactions. Despite sophisticated investigations utilizing cutting-edge technology and multidisciplinary research approaches, the Taos Hum remains as mysterious as when residents first reported it decades ago. While terrestrial mysteries like the hum confound scientists on Earth, equally puzzling signals reach us from the depths of space itself. Fast radio bursts, recent breakthrough discoveries. Millisecond bursts of radio energy from deep space have captivated astronomers since their first detection in 2007. These fast radio bursts arrive without warning, releasing tremendous amounts of energy in the blink of an eye before vanishing completely. Each burst lasts mere milliseconds, yet scientists estimate they occur roughly once every 10 seconds somewhere in the observable universe. The closest fast radio burst ever detected was discovered in 2024, originating from a galaxy just 3 billion light-years away. This relatively nearby burst provided unprecedented detail about the signal's characteristics and properties. Previous detections came from much more distant galaxies, making detailed analysis extremely challenging. The proximity of this burst allowed astronomers to study its structure with remarkable precision using multiple telescopes simultaneously. These cosmic events release staggering amounts of energy in incredibly short time frames. A single fast radio burst can emit more energy in milliseconds than our sun produces over several days of continuous nuclear fusion. To put this in perspective, the energy output equals what our sun generates during approximately 80 years of normal operation, compressed into a time span shorter than a human heartbeat. Scientists achieved a major breakthrough with the identification of FRB 2020-0120, E's source as a magnetar within a nearby galaxy. Magnetars are neutron stars possessing magnetic fields, trillions of times stronger than Earth's. These exotic objects represent some of the most extreme environments in the universe, where matter exists in states impossible to recreate on Earth. The magnetar connection provides crucial insights into the physical processes that might generate these powerful radio emissions. Some fast radio bursts repeat at irregular intervals while others appear only once, creating a puzzle that defies current theoretical models. Repeating bursts suggest their sources survived the initial emission event, while one-time bursts might indicate catastrophic destruction of their source objects. This fundamental difference challenges astronomers to develop separate explanations for what might actually be different types of phenomena. Advanced observations in 2024 detected fast radio bursts with complex polarization patterns revealing information about their source environments. These patterns indicate the presence of extreme magnetic fields that twist and bend radio waves as they travel through space. The polarization signatures suggest some bursts originate near black holes or in the aftermath of neutron star collisions where magnetic fields reach extraordinary intensities. The Canadian Hydrogen Intensity Mapping Experiment Telescope Array has cataloged over 1,000 fast radio bursts, revealing unexpected diversity in their properties. Some bursts show complex internal structure with multiple peaks, while others appear as simple pulses. The frequency ranges, durations, and repetition patterns vary dramatically, suggesting multiple mechanisms might be responsible for generating these signals. A controversial possibility exists that some fast radio bursts could represent artificial signals from advanced civilizations. While most scientists remain skeptical, the burst characteristics do not completely rule out technological origins. The energy requirements would demand technology far beyond current human capabilities, making this explanation highly speculative. Despite remarkable progress in detection and analysis, the fundamental mechanism producing fast radio bursts remains completely unknown. Yet, while we search for answers in distant galaxies, some of science's most perplexing mysteries exist much closer to home, hidden in the most ordinary aspects of human biology. Fingerprint Evolution 2025 Genetic Research. Every human being possesses completely unique fingerprints, yet science still cannot explain why we evolved these distinctive ridge patterns in the first place. These swirling lines and loops that cover our fingertips serve as perfect identification markers, but evolution did not anticipate the invention of forensic science. The mystery deepens when we consider that no two people share identical fingerprints, not even identical twins who develop from the same fertilized egg. Genetic studies conducted throughout 2025 have identified specific genes that control fingerprint ridge formation during fetal development. Researchers discovered that particular gene variants influence how skin cells organize themselves into ridge patterns between the 10th and 17th weeks of pregnancy. These genes regulate the expression of proteins that guide cellular migration and differentiation in developing fingertip skin. The research reveals that fingerprint formation follows predictable genetic pathways, yet the final patterns remain unique to each individual due to complex interactions between multiple genes. Experiments testing whether fingerprints actually improve grip have produced surprisingly mixed results that challenge conventional assumptions. Some laboratory studies show that fingerprint ridges enhance friction between fingertips and smooth surfaces, similar to tire treads on wet pavement. However, other carefully controlled experiments found no significant improvement in gripping ability when comparing smooth fingertips to ridged ones. These contradictory findings suggest that grip enhancement might not be the primary evolutionary purpose of fingerprints. New research on fingerprint sensitivity proposes that these ridge patterns might amplify vibrations for enhanced touch perception. Scientists discovered that fingerprint ridges create resonance effects when fingers contact textured surfaces, potentially magnifying subtle vibrations that help us detect fine textures and surface irregularities. This amplification could explain why humans possess such remarkable tactile sensitivity compared to other mammals with smooth fingertips. Comparative studies with other primates reveal that fingerprint complexity correlates directly with manual dexterity across different species. Humans possess the most complex fingerprint patterns and demonstrate the highest levels of fine motor control. Great apes show moderately complex ridge patterns with correspondingly advanced manipulation abilities. This correlation suggests that fingerprint evolution relates to the development of precise hand movements. A significant 2024 discovery revealed that fingerprint patterns can indicate susceptibility to certain genetic conditions. Researchers found that specific ridge configurations correlate with increased risk for congenital heart defects, chromosomal abnormalities, and developmental disorders. This connection between fingerprint patterns and genetic health opens new possibilities for early medical screening using non-invasive fingerprint analysis. Despite sharing identical DNA, identical twins develop different fingerprints during fetal development. This phenomenon occurs because fingerprint formation depends on environmental factors within the womb, including finger position, amniotic fluid flow, and pressure from surrounding tissues. These random environmental influences create unique ridge patterns even when genetic instructions remain identical. Despite remarkable genetic breakthroughs revealing the biological mechanisms of fingerprint formation, the evolutionary purpose of these unique patterns remains an open question. Yet, while we struggle to understand why our bodies develop these mysterious ridges, medical researchers have discovered that our minds possess the placebo effect, abilities to heal our bodies through belief alone. Fake treatments produce real medical improvements in ways that continue to baffle researchers worldwide. Sugar pills relieve genuine pain. Saline injections reduce nausea. Sham surgeries heal chronic conditions. These aren't cases of confused patients or wishful thinking. These are measurable biological changes that occur when people believe they're receiving effective treatment, even when the treatment contains no active ingredients whatsoever. Neuroimaging studies conducted throughout 2024 revealed exactly how placebo treatments activate the brain's natural pain relief systems. Advanced brain scanning technology shows that placebo pills trigger the release of endorphins and other natural painkillers in regions like the prefrontal cortex and periaqueductile gray. These aren't imaginary responses. They represent genuine neurochemical changes that reduce pain perception at the cellular level. The brain literally manufactures its own medicine when it expects relief, creating biological effects that mirror those of actual pharmaceutical drugs. Placebo effects have grown significantly stronger over the past decade, creating serious complications for drug trials. Modern patients show more dramatic improvements from inactive treatments than previous generations, making it increasingly difficult to prove that new medications work better than placebos. Pharmaceutical companies now struggle to demonstrate drug effectiveness because placebo responses have become so powerful that they often rival the effects of active treatments. Open-label placebo trials represent one of medicine's most surprising discoveries. Patients who know they're receiving fake treatments still experience real improvements in their symptoms. Researchers inform participants that their pills contain no active ingredients, yet these honest placebos continue producing measurable health benefits. This phenomenon challenges everything scientists thought they understood about how placebos work, suggesting that conscious belief in treatment effectiveness isn't necessary for biological responses to occur. Placebo responses vary dramatically between cultures and individuals, revealing complex patterns that researchers are only beginning to understand. Patients in some countries respond more strongly to placebo injections, while others show greater improvement from placebo pills. Individual genetic variations in dopamine and opioid receptors significantly influence placebo effectiveness, creating biological differences in how people respond to expectation-based treatments. Studies on the nocebo effect conducted in 2025 demonstrate how negative expectations can cause real physical harm. Patients who anticipate side effects often experience those exact symptoms, even when receiving inactive treatments. Warning patients about potential adverse reactions can actually trigger the problems doctors hope to prevent, creating a troubling paradox where medical honesty might harm patient outcomes. Research documenting placebo effects in animals challenges purely psychological explanations for this phenomenon. Laboratory animals show measurable improvements from inactive treatments, suggesting that biological mechanisms beyond conscious expectation contribute to placebo responses. Despite understanding some mechanisms behind placebo responses, the full power of expectation over biology remains mysterious. Modern medicine can map brain changes during placebo treatment and identify genetic factors that influence responses, yet the fundamental question persists. The mind's ability to create physical healing through belief alone represents just one example of how reality operates in ways that defy our everyday understanding of cause and effect. Quantum entanglement mechanics' current understanding